Imagine standing in your backyard on the clearest night you can remember, gazing up at stars that seem to shimmer and dance through the restless air above. You squint, trying to see more clearly, wishing you could somehow brush away the invisible veil that blurs the cosmic vista overhead. For thousands of years, every human who has ever looked up at the night sky has felt this same gentle frustration, this longing to see beyond the trembling atmosphere that wraps our world like a protective blanket, yet also like a frosted window between us and the universe. Hello and welcome to the Sleepy Astronomer. Tonight, we're drifting into the story of humanity's most beloved eye in the sky, the Hubble Space Telescope. A story that begins not with triumph, but with an ancient dream and a spectacular, very public failure that somehow transformed into one of our species' greatest achievements. Whether you're tucked into bed, curled up on a favourite chair, or perhaps lying back where you can glimpse the night sky through a window, I'm so glad you're here. If you're settling in for the first time, welcome aboard our gentle journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Tonight, our story begins in 1923 with a visionary named Hermann Oberth, who dared to imagine what seemed impossible, a telescope that could escape Earth's atmospheric embrace entirely. But it truly takes flight in 1946 with Lyman Spitzer, an astronomer who wrote a paper that would change everything, describing 4 simple advantages of placing a telescope in space: no atmospheric distortion, access to all wavelengths of light, no weather delays, and the ability to observe continuously without the interruption of sunrise. There's something deeply human about this dream of perfect vision. Ancient myths speak of all-seeing gods who could peer through any veil, while Renaissance astronomers strained their eyes through primitive telescopes, forever frustrated by the dancing air that softened every cosmic detail. Even Galileo, peering through his revolutionary spyglass at Jupiter's moons, must have wondered what wonders might be revealed if only the atmosphere would hold perfectly still. But space, as we would discover, presents its own challenges. How do you power a telescope 350 miles above Earth? How do you point it with precision finer than the width of a human hair, seen from 2 miles away? How do you communicate with it, repair it when things go wrong, and keep it operating for years in the harsh environment of space, where there's no air to breathe, no gravity to anchor you, and radiation that would be lethal to unprotected human eyes? The answers to these questions would take decades to discover, involve thousands of brilliant minds, survive political battles and budget cuts, and ultimately lead to a moment in 1990 when humanity held its breath as the most sophisticated telescope ever built was released from a space shuttle's cargo bay to begin its eternal vigil among the stars. Little did we know that this moment of triumph would quickly turn to despair, then to one of the most dramatic rescue missions in space exploration history, and finally to a love affair between humanity and a machine that has shown us the universe as we never imagined it could be seen. So, find your most comfortable position, perhaps with a warm drink nearby and the lights dimmed low. Take a deep breath and let your mind drift upward, beyond the roof over your head, beyond the clouds, beyond the thin shell of air that surrounds our world. Out there, in the perfect darkness of space, a telescope no larger than a school bus continues its patient watch, sending us postcards from the edge of time itself. Tonight, we'll discover how a dream became reality, how failure became triumph, and how one telescope changed not just astronomy, but the way our entire species sees itself in the vast, beautiful, and mysterious universe we call home. Picture yourself as Galileo Galilei on a clear night in 1609, holding your handcrafted telescope, little more than 2 lenses in a tube, and pointing it toward Jupiter. Through the eyepiece you see something that makes your heart race. 4 tiny points of light dancing around the giant planet, moons that no human eye had ever glimpsed before. But even as you sketch these revolutionary discoveries, you notice how the images shimmer and blur, how the atmosphere above your head seems to breathe and pulse, softening every celestial detail like looking through water. This is the fundamental problem that has haunted astronomy since humans first turned optical instruments skyward. Our atmosphere, that precious blanket of air that keeps us alive, also acts like a restless ocean above our heads, constantly in motion, bending and scattering starlight in endless, unpredictable ways. Stars that are actually steady points of light appear to twinkle and dance. Planets blur into fuzzy disks, and the finest details of cosmic wonders remain forever just beyond our reach, tantalizingly close, yet impossibly distant. For over 3 centuries, astronomers learned to live with this limitation. They built larger telescopes, ground more perfect mirrors, and developed clever techniques to squeeze every photon of clarity from their earthbound observations. They learned to work with the atmosphere's moods, how it steadies on cold, dry nights and grows restless when warm air rises from sun-heated ground. Some moved their telescopes to mountain tops, above much of the water vapour and turbulence. Others waited patiently for those rare moments when the air held perfectly still, allowing them to glimpse the universe with startling clarity. But there were always those who dreamed of something more radical. What if, instead of trying to work around the atmosphere, we could escape it entirely? The first person to seriously propose this seemingly impossible idea was Hermann Oberth, a Romanian-born physicist who in 1923 wrote about rockets and space travel with the kind of visionary thinking that seemed like pure fantasy to most of his contemporaries. Tucked away in his technical discussions of rocket propulsion and orbital mechanics was a brief but revolutionary suggestion. Why not place a telescope in space, above the atmosphere entirely? At the time, this seemed absurdly impractical. In 1923, rockets were crude, unreliable contraptions that could barely lift themselves off the ground, let alone carry delicate scientific instruments into orbit. The very concept of a stable orbit around Earth was still largely theoretical. Most astronomers, focused on the practical challenges of building ever larger ground-based telescopes, probably dismissed Oberth's space telescope idea as the stuff of science fiction. But ideas, once planted, have a way of taking root in unexpected places. 23 years later, in 1946, a young American astronomer named Lyman Spitzer Jr. was sitting in his office at Yale University when he decided to take Oberth's wild idea seriously. Spitzer was already establishing himself as a brilliant theoretical astrophysicist, but he was also a man who thought in practical terms about the tools needed to unlock the universe's secrets. That year, Spitzer wrote a paper with the straightforward title, Astronomical Advantages of an Extraterrestrial Observatory. It's a document that reads today almost like a prophecy, laying out in clear, logical language exactly why space-based astronomy would revolutionize our understanding of the cosmos. The paper is only 7 pages long, but those 7 pages would eventually lead to the Hubble Space Telescope and transform how humanity sees itself in the universe. Spitzer identified 4 key advantages that a space-based telescope would have over any ground-based instrument, no matter how large or sophisticated. First, and most obviously, there would be no atmospheric distortion. Stars would appear as perfect points of light rather than twinkling, dancing images. Planets would show crisp details instead of blurry approximations. Galaxies would reveal structures that remain forever hidden when viewed through our restless atmosphere. Second, a space telescope could observe across the entire electromagnetic spectrum. Our atmosphere acts like a selective filter, blocking most ultraviolet light, many infrared wavelengths, and virtually all X-rays and gamma rays from reaching the ground. These invisible forms of light carry crucial information about stellar births and deaths, black holes, and the high-energy processes that shape the universe. From space, all of this previously hidden information would be accessible for the first time. Third, there would be no weather. No clouds rolling in just as a rare astronomical event begins. No humidity fogging delicate instruments. No wind vibrations shaking the telescope structure. Space offers perfect weather all the time, eternal darkness punctuated only by the steady light of stars. And fourth, continuous observation would be possible. Ground-based telescopes can only work at night, and even then they're limited by the time an object spends above the horizon. A space telescope could observe targets for hours, days, or even weeks without interruption, building up incredibly detailed images and spectra that would be impossible from Earth. Reading Spitzer's paper today, these advantages seem obvious, but in 1946 they represented a leap of imagination that few were prepared to make. The space age hadn't yet begun. Sputnik was still 11 years in the future. The technology needed to build, launch, and operate a telescope in space didn't exist, and wouldn't for decades. Yet Spitzer possessed something essential for any revolutionary idea: persistence combined with patience. He understood that transforming astronomy would require not just scientific vision, but also political skill, engineering innovation, and the kind of long-term thinking that spans decades rather than years. There's something deeply moving about this kind of scientific dreaming. Throughout history, there have always been individuals who looked beyond the immediate limitations of their time to imagine what might be possible with tools that didn't yet exist. They're the intellectual ancestors of every major technological advance. People who dared to ask, "What if?" when everyone else was focused on how things are. In ancient Greece, philosophers imagined that all matter was made of tiny, invisible particles they called atoms. They had no way to see these particles, no instruments to detect them, no mathematics to describe their behavior. Yet their dream of atomic reality would eventually become the foundation of modern chemistry and physics. Similarly, Renaissance artists like Leonardo da Vinci sketched flying machines centuries before the internal combustion engine made powered flight possible. They understood something profound: that human imagination, when properly directed, can reach across centuries to touch future realities. Spitzer's vision of space-based astronomy belonged to this tradition of transformative dreaming. He could see, with startling clarity, how escaping Earth's atmosphere would revolutionize our understanding of the cosmos. But he also understood that making this vision real would require building support among fellow scientists, convincing government agencies to fund the research, and developing technologies that existed only in theory. The cultural significance of this dream runs deeper than mere scientific advancement. For thousands of years, humans have told stories about all-seeing gods and magical instruments that could reveal hidden truths. The Greek myth of Argus, the giant with 100 eyes who could see everything, reflects our ancient longing for perfect, unobstructed vision. Medieval legends speak of crystal balls and magic mirrors that could show distant places and future events. Even fairy tales like Snow White feature mirrors that possess supernatural knowledge. Mirror, mirror on the wall, Who's the fairest of them all? What Spitzer was proposing was, in many ways, the technological fulfillment of these ancient dreams. A space telescope would be humanity's all-seeing eye, capable of looking deeper into space and time than any ground-based instrument could hope to achieve. It would be our crystal ball, revealing the hidden architecture of the cosmos and perhaps showing us visions of the universe's distant past and far future. But unlike the magical instruments of myth and legend, Spitzer's space telescope would be built on solid scientific principles and engineering expertise. It would achieve its miraculous vision not through supernatural powers, but through the application of human knowledge and ingenuity to overcome the fundamental limitation that had constrained astronomy since Galileo's time. The technical challenges were staggering. A space telescope would need to operate in an environment more hostile than any place on Earth. In the vacuum of space, there's no air to carry away excess heat or to provide convective cooling. Electronics that work perfectly at room temperature can fail catastrophically when subjected to the extreme temperature swings between sunlight and shadow. Materials that are stable in Earth's atmosphere can outgas in vacuum, contaminating sensitive optical surfaces. Power would be another enormous challenge. Ground-based telescopes simply plug into the electrical grid. A space telescope would need to generate its own power, probably using solar panels, and store enough energy in batteries to continue operating when Earth's shadow blocks the sun. The power systems would need to work reliably for years, perhaps decades, without any possibility of repair or replacement. But perhaps the most daunting challenge was precision pointing. Ground-based telescopes can use the horizon, gravity, and familiar star patterns for reference. A space telescope tumbling through orbit at thousands of miles per hour would need to point at tiny targets in the sky with incredible accuracy and hold that pointing stable for hours at a time. The level of precision required would be like trying to keep a laser beam focused on a dime from 2 miles away while riding a roller coaster. Communication presented yet another set of obstacles. A space telescope would need to transmit enormous amounts of data, detailed images and spectra across hundreds of miles of empty space to receivers on Earth. In 1946, television was still a novelty, and the idea of transmitting high-resolution images from orbit was purely theoretical. And underlying all these technical challenges was the fundamental question of access. If something went wrong with a space telescope, and in the harsh environment of space, something almost certainly would go wrong, how could it be repaired? Ground-based telescopes can be maintained by technicians who drive to the observatory, but a space telescope would be permanently beyond reach of conventional repair methods. These were the problems that kept most astronomers focused on ground-based instruments throughout the 1940s and 1950s. The challenges seemed so overwhelming that many considered space-based astronomy an interesting theoretical exercise with little practical relevance. Why worry about hypothetical space telescopes when there was so much productive work to be done with existing ground-based instruments? But Spitzer and a growing number of visionary colleagues understood something that would prove prophetic. The advantages of space-based astronomy were so enormous that they would justify almost any level of technical difficulty and expense. The scientific return from a single space telescope could exceed the combined output of all ground-based observatories. As the 1950s progressed and the space age began with Sputnik's launch in 1957, Spitzer's ideas started to seem less like fantasy and more like inevitable destiny. If humans could put satellites in orbit, surely they could put telescopes there too. The question was no longer whether space-based astronomy was possible, but when it would become reality and what form it would take. The dream of perfect celestial vision was about to begin its long journey from imagination to reality, though that journey would prove far more complex, frustrating, and ultimately triumphant than even Spitzer could have imagined. The universe was waiting, patient and eternal, for humanity to build the eyes necessary to see it clearly at last. Imagine walking into the cleanest room you've ever seen, so clean that a single speck of dust would be considered a catastrophe. The air itself has been filtered and refiltered until it contains fewer particles than the space between planets. Workers move slowly and deliberately in white bunny suits that cover every inch of their bodies, their faces hidden behind clear visors, their hands sealed in sterile gloves. This is where dreams become reality, where the ethereal vision of a space telescope transforms into precision-crafted metal, glass, and electronics that will soon ride a pillar of fire into the cosmos. By the 1970s, Lyman Spitzer's patient advocacy had begun to bear fruit. The dream of a space telescope was no longer the fantasy of a few visionaries. It had become an official NASA program called the Large Space Telescope, later to be renamed in honor of Edwin Hubble, the astronomer who had revealed that our universe is far larger and stranger than anyone had imagined. But transforming a beautiful concept into actual hardware, capable of surviving the journey to space and operating flawlessly for years, would prove to be one of the most complex engineering challenges ever undertaken. The heart of any telescope is its primary mirror, the carefully curved surface that gathers precious photons from distant stars and focuses them into sharp images. For the space telescope that would become Hubble, this mirror needed to be absolutely perfect, more perfect in fact than any mirror ever created for astronomical use. Ground-based telescopes can compensate for small imperfections in their mirrors through various techniques, but a space telescope operating hundreds of miles above Earth would have no such luxuries. Its mirror would need to be shaped to an accuracy of a few millionths of an inch, smooth enough that if it was scaled up to the size of Earth, the largest bump would be only 6 feet high. The specifications were breathtaking in their precision. The mirror would measure 2.4 meters across, about 8 feet, and weigh nearly a ton. Its surface would be coated with a thin layer of aluminum only a few atoms thick, protected by an even thinner layer of magnesium fluoride to prevent tarnishing. When complete, it would be capable of focusing starlight with such precision that it could theoretically spot a firefly on the moon. Two companies competed for the honor and enormous responsibility of creating this miraculous mirror: Corning Glass Works and Perkin-Elmer Corporation. Both were titans of precision optics, with decades of experience crafting mirrors for ground-based telescopes. But this project pushed far beyond anything either had attempted before. The mirror would need to maintain its perfect shape not just in Earth's gravity, but in the weightless environment of space where thermal expansion and contraction from sunlight and shadow could distort even the most carefully crafted surface. Corning proposed to make the mirror from their ultra-low expansion glass, a material so stable that temperature changes barely affected its dimensions. Their approach was methodical, conservative, building on proven techniques refined over generations of mirror makers. Perkin-Elmer, however, offered a more ambitious solution. They would use a lighter glass substrate and employ computer-controlled polishing machines to achieve unprecedented precision. Their proposal promised not just a perfect mirror, but a revolution in how large optical surfaces could be manufactured. NASA chose Perkin-Elmer's approach, a decision that would prove both inspired and catastrophic in ways no one could foresee. The company's engineers and craftsmen began the delicate process of transforming a rough glass blank into the most precise mirror ever created. Using diamond-tipped tools and computer guidance, they slowly carved away microscopic layers of glass, checking and rechecking their progress with laser interferometers that could measure variations smaller than the wavelength of light itself. The process was mesmerizing in its precision. Imagine watching a sculptor work on a statue so detailed that every grain of marble must be positioned perfectly, except that this sculptor was working with tolerances measured in nanometers, distances so small that individual atoms become significant. The polishing alone took months, with the mirror's surface gradually approaching the theoretical perfection that space-based astronomy demanded. But the mirror was only the beginning. Around this gleaming heart of the telescope, engineers had to build a spacecraft capable of surviving the brutal environment of space, while maintaining the stability of a fine Swiss watch. The challenge was like building a luxury sedan that could operate perfectly while being shaken, frozen, baked, and bombarded with radiation, all while maintaining precision that would make a watchmaker weep with envy. The telescope's main body, or optical telescope assembly, was crafted from a special graphite epoxy composite material that would remain dimensionally stable across the extreme temperature swings of space. In sunlight, one side of the telescope could reach temperatures hot enough to boil water, while the shadowed side might be colder than Antarctica in winter. The structure had to accommodate these extremes without flexing enough to blur the focus of that perfect mirror. Solar panels would provide power, but these weren't the simple flat panels you might see on a rooftop. They were engineered marvels designed to track the sun with the precision of a sunflower while protecting the telescope's sensitive instruments from solar radiation. The panels could be rolled up for launch and then deployed in space, like mechanical flowers opening to catch the light. Perhaps the most challenging aspect of the entire design was the pointing system. A space telescope tumbling through orbit needs to aim at targets that appear smaller than a period on this page when viewed from 350 miles away. The system would need to lock onto guide stars and hold that position steady to within 0.007 arcseconds, an angle so small that it's equivalent to focusing on a dime from 200 miles away. This precision would be achieved through a combination of gyroscopes, reaction wheels, and fine guidance sensors. The gyroscopes, spinning at thousands of revolutions per minute, would sense any unwanted motion. The reaction wheels, essentially computer-controlled spinning discs, would counteract that motion by speeding up or slowing down, and the fine guidance sensors would lock onto carefully selected stars, using their positions to maintain perfect pointing for hours at a time. The scientific instruments that would ride along with this precision platform were marvels in their own right. The wide-field and planetary camera would serve as Hubble's primary eye, capable of taking images across a range of wavelengths from ultraviolet to near-infrared. Spectrographs would analyze the light from distant objects, breaking it down into its component colors to reveal the chemical composition, temperature, and motion of stars and galaxies. Each instrument was essentially a complete observatory in miniature, packed with more computing power than existed in entire universities just decades earlier. They were designed not just to observe the universe, but to do so with a level of sensitivity and precision that would have seemed magical to earlier generations of astronomers. The cultural weight of this endeavor was immense. Here was humanity's attempt to craft a perfect eye, something that connected to our deepest mythologies about vision and knowledge. The ancient Egyptians believed that the eye of the god Horus could see everything in the heavens and on earth. Norse mythology spoke of Odin's ravens, Hugin and Munin, who flew across all the 9 worlds each day to bring back knowledge of everything that transpired. Now, In gleaming metal and glass, engineers were building humanity's own all-seeing eye. The symbolism wasn't lost on those working on the project. Many of the engineers and technicians spoke of feeling a weight of responsibility that went beyond mere technical specifications. They were crafting not just an instrument, but a representation of human aspiration, our species' determination to see beyond the limitations that had confined us since we first gazed upward in wonder. There's something profoundly moving about the level of craftsmanship that went into every component. Master opticians hand-polished mirror surfaces using techniques passed down through generations, while simultaneously employing cutting-edge computer modeling to achieve previously impossible precision. Technicians in clean rooms worked with the concentration of medieval monks illuminating manuscripts, knowing that a moment's carelessness could ruin months of painstaking work. The clean room itself had its own mythology among the workers. Stories were told of technicians who could spot contamination invisible to others, of polishing specialists whose hands could feel imperfections measured in atoms. These weren't just factory workers assembling a product. They were artisans participating in something that felt almost sacred, the creation of humanity's first true window to the cosmos. Even the smallest components received this level of attention. Screws were made from specially selected alloys and tested individually. Wire connections were soldered by technicians whose steady hands had been trained for years. Electronic components were burned in, operated continuously for weeks to identify any parts that might fail early in the telescope's mission. Nothing was left to chance, because everyone understood that once Hubble reached orbit, there would be no second chances. The integration process, assembling all these perfect components into a working whole, took place in chambers that were cleaner than operating rooms. Teams of specialists wearing protective suits moved like dancers in slow motion, carefully mating optical assemblies with electronic systems, checking and double-checking every connection. The entire telescope was tested and retested under conditions that simulated the vacuum, radiation, and temperature extremes of space. Vibration tests subjected the complete telescope to forces that would tear apart most earthly structures, ensuring that it could survive the violent ride to orbit aboard a space shuttle. Thermal vacuum tests placed the entire assembly in chambers that could reproduce the airless, temperature-swinging environment of space. Every system was pushed to its limits and beyond, because once the telescope reached orbit, there would be no opportunity for repairs, or so everyone believed at the time. The optical tests were perhaps the most critical of all. Using sophisticated equipment that could simulate starlight, engineers verified that the mirror and instruments would work together to produce the crisp, detailed images that astronomers around the world were eagerly anticipating. These tests suggested that everything was working perfectly, that humanity's first great space observatory would exceed even the most optimistic expectations. As the 1980s progressed and launch approached, excitement within the astronomical community reached fever pitch. Hubble would be capable of seeing objects 50 times fainter than the best ground-based telescopes. With resolution limited only by the fundamental physics of light, rather than by atmospheric turbulence, it would peer deeper into space, and therefore further back in time, than any instrument ever created. The telescope that emerged from this decade-long process of design and construction was a thing of beauty as well as science. Gleaming white and silver, bristling with high-tech appendages, it looked like something from the most optimistic dreams of the future. At 43 feet long and weighing 11 tons, it was about the size of a large school bus, packed with more technological sophistication than most spacecraft and more precision than the finest Swiss chronometer. But perhaps most remarkably, this mechanical marvel represented the focused efforts of thousands of people, engineers, technicians, scientists, and visionaries, all working toward a single goal, giving humanity the perfect celestial vision that our species had dreamed of since we first looked up at the stars and wondered what secrets they might hold. The dream that had begun in Lyman Spitzer's mind 4 decades earlier was now real, tangible, ready to ride fire into the darkness and show us the universe as we had never seen it before. The only question that remained was whether this magnificent machine would fulfill the promises that had sustained its creators through years of painstaking work, political battles, and technical challenges that had pushed the boundaries of what seemed possible. Soon, the world would find out, and the answer would be both more heartbreaking and more triumphant than anyone dared imagine. Picture the moment just before dawn on April 24th, 1990, when the Space Shuttle Discovery sits on its launch pad like a patient white bird, exhaling wisps of vapor into the cool Florida air. Inside the cargo bay, nested like a precious gift in layers of protective foam and metal, lies the Hubble Space Telescope, humanity's most sophisticated eye, ready for its journey beyond the atmospheric veil that has limited our vision since the dawn of astronomy. The launch itself is poetry in motion, a controlled explosion that lifts 4.5 million pounds of metal, fuel and dreams away from Earth's gravity well. For 8.5 minutes, Discovery climbs through the layers of atmosphere that have frustrated astronomers for centuries, through the troposphere where weather lives, past the stratosphere where ozone filters ultraviolet light, beyond the mesosphere where meteors burn up in brilliant streaks. Finally, the engines fall silent, and the shuttle glides into the perfect darkness of space, carrying with it the hopes of generations of stargazers who had dreamed of seeing the universe clearly at last. The deployment itself was a masterpiece of orbital choreography. Astronauts used the shuttle's robotic arm to lift Hubble from the cargo bay with the delicacy of handling a soap bubble, each movement slow and deliberate. There's something almost ceremonial about watching a space telescope being released into its eternal orbit, like setting a magnificent bird free to soar among the stars. As Discovery slowly backed away, Hubble spread its solar panel wings and began its solitary dance around Earth, one orbit every 97 minutes, forever beyond the reach of the atmosphere that had constrained human vision since our species first looked up at the night sky. Those first few weeks after deployment felt like holding your breath before opening a long-awaited gift. Engineers carefully activated Hubble systems one by one, like slowly waking a sleeping giant. The solar panels unfurled perfectly, drinking in unfiltered sunlight. The pointing system came online, using guide stars to orient the telescope with precision finer than a human hair. The instruments powered up, their detectors cooling to temperatures hundreds of degrees below zero, to achieve the sensitivity needed to capture whispers of light from the edge of the universe. The astronomical community waited with the patience of parents watching a child take their first steps. Every successful system activation was celebrated quietly, every small milestone bringing them closer to the moment when Hubble would open its eye and show humanity the cosmos as no earth-bound telescope ever could. The anticipation was almost tangible. Decades of planning, years of construction, months of testing, all leading to this moment when the universe would reveal itself in unprecedented clarity. But first light, that magical moment when a new telescope takes its first photograph, would prove to be both triumph and heartbreak wrapped in a single devastating image. On May 20th, 1990, nearly a month after launch, Hubble pointed its mirror toward a star cluster and captured its first focused image. The photograph that came back to Earth was both beautiful and terrifying. The stars were there, glowing against the velvet darkness of space, but something was wrong. Each point of light was surrounded by a soft halo of scattered light, like street lamps viewed through fog. The images were clearer than anything possible from Earth's surface, but they fell far short of the crisp perfection that Hubble had been designed to achieve. At first, there was cautious optimism. Perhaps the images could be sharpened through computer processing. Maybe the telescope's mirrors needed time to settle after the launch. Early reports spoke hopefully of better than expected performance, and some astronomers genuinely believed that even these slightly blurry images would revolutionize their field. The view from space, after all, was still dramatically superior to anything achievable from the ground. But as days turned to weeks and more images arrived, the terrible truth became undeniable. Hubble's mirror, that masterpiece of precision crafted over years by master opticians, suffered from a flaw so fundamental that no amount of computer processing could correct it. The mirror had been ground to the wrong shape, not by much, just 2.2 micrometers, about 1/50th the width of a human hair. But, in the unforgiving realm of precision optics, this tiny error was catastrophic. The technical term for the problem was spherical aberration. Instead of focusing starlight to perfect points, the mirror spread each star's light into a fuzzy disk surrounded by rings of scattered photons. It was as if someone had tried to create a perfect lens, but had made it just slightly the wrong shape, turning what should have been sharp vision into something that resembled looking through the bottom of a bottle. The diagnosis hit the astronomical community like a physical blow. This wasn't a minor calibration issue that could be fixed with software updates. This was a fundamental optical flaw that rendered the most expensive scientific instrument ever built only marginally better than telescopes that had cost a fraction of its $1.5 billion budget. The dream of perfect celestial vision, nurtured for decades and crafted with unprecedented precision, had been shattered by an error smaller than a bacterium. The investigation that followed read like a forensic analysis of how human systems can fail in the most subtle and devastating ways. At Perkin-Elmer, the company responsible for grinding Hubble's mirror, quality control had been meticulous, except for one crucial oversight. The null corrector, the complex optical system used to test the mirror's shape during polishing, had been assembled incorrectly. A single lens in the testing apparatus had been positioned 1.3 millimeters, about the thickness of a penny, from where it should have been. This tiny displacement had fooled the testing equipment into believing that an incorrectly shaped mirror was actually perfect. For months, skilled craftsmen had polished Hubble's primary mirror, using the faulty null corrector as their guide, slowly grinding the glass into a shape that matched the test equipment rather than the theoretical ideal that space-based astronomy required. The irony was cruel. The mirror had been manufactured with extraordinary precision, just precision applied to the wrong specification. What makes this failure even more poignant is that there were signs, small inconsistencies that might have revealed the problem, if anyone had thought to look for them. A backup test, using different equipment, had shown subtle discrepancies, but these warnings were dismissed as minor calibration issues. The culture of precision that had driven the entire project became, in this one crucial instance, a source of false confidence. The numbers looked perfect, so everyone assumed the mirror was perfect too. The media response was swift and merciless. Headlines across the globe proclaimed Hubble a $1.5 billion blunder. Late-night comedians found endless material in the concept of a nearsighted telescope that needed cosmic eyeglasses. Editorial cartoons showed Hubble wearing thick spectacles or squinting at distant stars. The project that was supposed to demonstrate American technological leadership had become an international embarrassment. The mythology of technological hubris seemed to write itself. Here was humanity reaching beyond its grasp, attempting something so ambitious that failure was perhaps inevitable. The comparison to the Tower of Babel was irresistible to commentators, mortals trying to build their way to heaven, only to have their efforts confounded by their own limitations. Scientists who had devoted their careers to space-based astronomy found themselves defending not just a broken telescope, but the entire concept of ambitious scientific endeavours. For the astronomers who had waited decades for this moment, the disappointment was deeply personal. Lyman Spitzer, now in his late 70s, watched his life's work become the subject of ridicule. Scientists who had planned entire research programs around Hubble's expected capabilities suddenly faced the prospect of careers derailed by optical imperfection. Graduate students who had hoped to use Hubble data for their dissertations wondered if they should change fields entirely. Yet even in the depths of this technological disaster, there were glimmers of hope that would prove prophetic. The images that Hubble produced, while flawed, were still better than anything achievable from Earth's surface. The resolution, even compromised by spherical aberration, surpassed ground-based telescopes by significant margins. More importantly, the spherical aberration was predictable and mathematically well understood. Computer processing could partially compensate for the optical flaw, extracting useful scientific data from the blurred images. The first successful science observations came from astronomers who learned to work with Hubble's limitations rather than against them. By using sophisticated image processing techniques, they could deconvolve some of the scattered light, essentially reversing the mathematical effects of the mirror's incorrect shape. The results weren't perfect, but they were scientifically valuable. Stars that appeared as fuzzy halos could be restored to something approaching point sources. Galaxy structures that were smeared by optical aberration could be partially reconstructed. Some astronomers, instead of joining the chorus of despair, began to see opportunity within the crisis. The mirror's shape was wrong, but it was wrong in a consistent, measurable way. Every photon that struck the mirror was misbehaved in exactly the same fashion, following optical laws that could be precisely calculated and potentially corrected. If you understood exactly how the light was being scattered, you could potentially develop techniques to gather it back together. It would be like learning to read text through a specific kind of distorted glass, difficult but not impossible. The engineering teams at NASA, meanwhile, were already thinking beyond the immediate crisis toward an audacious solution. Hubble had been designed with serviceability in mind, anticipating that astronauts might need to replace instruments or perform maintenance during its operational life. The telescope's modular design meant that major components could be removed and replaced, assuming you had astronauts skilled enough to perform precision work while wearing bulky spacesuits and using tools designed for the vacuum of space. What if, instead of accepting defeat, they could develop a way to correct the optical flaw in space? What if they could build corrective optics, essentially a giant contact lens for Hubble, and install it during a servicing mission? The concept was breathtakingly ambitious. Send astronauts on a mission more complex than any ever attempted to install corrective optics in a telescope orbiting 350 miles above Earth. It would be like performing precision eye surgery while wearing bulky gloves, using tools designed for a completely different purpose in an environment where a single mistake could be catastrophic. The cultural narrative that emerged from Hubble's initial failure touched on themes deeper than mere technological disappointment. This was about the human condition itself, our tendency to reach for perfection, only to be humbled by our own limitations. Yet it was also about something more hopeful, our remarkable ability to adapt, to learn from failure, and to transform disaster into triumph through persistence and ingenuity. In the months that followed first light, as engineers worked around the clock to develop solutions and astronomers learned to extract science from flawed images, Hubble began to embody a different kind of inspiration. It became a symbol not of human infallibility, but of human resilience. The telescope that was supposed to show us the universe with perfect clarity would instead teach us something perhaps more valuable, that even our most ambitious dreams can survive the most devastating setbacks. The broken telescope continued its patient orbit, its flawed mirror gathering light from distant stars and galaxies, waiting for the most audacious repair mission in the history of space exploration. And slowly, quietly, the astronomical community began to believe that their shattered dream might yet be restored to something even more beautiful than they had originally imagined. As we'll discover, sometimes the most profound successes emerge not from perfect execution, but from the courage to face our failures directly and transform them into something greater than we initially dared to dream. Picture yourself floating in the cargo bay of a space shuttle 350 miles above Earth, looking up at the Hubble Space Telescope suspended against the infinite black of space like a mechanical prayer waiting to be answered. Your spacesuit is bulky, your gloves make fine work nearly impossible, and you're about to attempt the most complex repair job ever undertaken in the vacuum of space. Below you, Earth turns slowly in its ancient rhythm, displaying the blues and whites and browns of home, while above, the stars wait with infinite patience for humanity to fix the eye it had built to see them clearly. This was the scene in December 1993, when 7 astronauts aboard the Space Shuttle Endeavour embarked on what NASA called Servicing Mission 1, though history would remember it as one of the most audacious rescue operations ever attempted. For 3.5 years, Hubble had been circling Earth with its flawed vision, producing images that, while scientifically valuable, fell far short of the revolutionary clarity that had been promised. Now, in an unprecedented feat of orbital surgery, astronauts would attempt to give the telescope the equivalent of corrective lenses, restoring sight to humanity's most important eye in the sky. The mission had been years in the making, involving thousands of engineers, scientists and technicians working around the clock to design solutions that had never been attempted before. The primary fix would come in the form of COSTAR, the Corrective Optics Space Telescope axial replacement, a device so ingeniously designed it seemed almost magical in its simplicity. COSTAR would be installed inside Hubble, where it would intercept the scattered light from the flawed primary mirror and redirect it with perfect precision to the telescope's scientific instruments. The concept behind COSTAR was elegantly straightforward, even if its execution would prove extraordinarily challenging. Think of it as creating a set of corrective lenses that could be positioned precisely in the path of Hubble's light beam, compensating for the spherical aberration in the primary mirror by introducing an equal and opposite distortion. The scattered light that had been Hubble's curse would be gathered up and focused into the sharp points that space-based astronomy required. But COSTAR could only feed corrected light to some of Hubble's instruments. The Wide Field and Planetary Camera, Hubble's primary imaging system, would need to be replaced entirely with a new version that had corrective optics built directly into its design. The Wide Field and Planetary Camera 2, or WFPC-2, as engineers called it, was essentially a new telescope within a telescope, designed to work perfectly with Hubble's imperfect mirror. The engineering challenges of performing precision optical work in space were staggering. On Earth, installing delicate scientific instruments requires clean rooms, stable surfaces, and the ability to make tiny adjustments with steady hands. In space, there are no clean rooms, just the infinite vacuum where a dropped tool becomes a piece of orbital debris traveling at thousands of miles per hour. There are no stable surfaces. Everything is in constant motion, orbiting Earth at 17,500 miles per hour. And there are no steady hands, just astronauts wearing bulky spacesuits, trying to manipulate tools designed for an environment unlike anything on Earth. The astronaut training for this mission was unlike anything NASA had ever attempted. At the Marshall Space Flight Center in Alabama, a full-scale mock-up of Hubble was submerged in a giant swimming pool where astronauts could practice the repair procedures in the closest earthly approximation to weightlessness. For months, they rehearsed every step of the complex choreography that would be required to give Hubble new vision. The underwater training sessions had an almost ritualistic quality. Suited astronauts would descend into the blue depths of the neutral buoyancy laboratory, where Hubble's mock-up waited like a patient in an underwater operating room. Scuba diving safety officers watched carefully as the astronauts practiced removing panels, installing instruments, and connecting cables with the kind of precision that would be required 350 miles above Earth. Each procedure was rehearsed until it became second nature, until muscle memory could guide their work even when wearing the bulky gloves that made fine manipulation so difficult. The cultural significance of this mission extended far beyond its technical challenges. Here was humanity refusing to accept defeat, demonstrating the kind of persistence and ingenuity that had carried our species from caves to the stars. The mythology was irresistible, brave heroes venturing into the cosmic darkness to heal a wounded mechanical giant, restoring sight to the blind eye that would show us wonders beyond imagination. There's something deeply moving about the human capacity to transform failure into triumph through sheer determination and skill. Throughout history, our greatest achievements have often emerged not from perfect execution, but from our ability to adapt, improvise, and overcome seemingly impossible obstacles. The Hubble repair mission embodied this spirit, demonstrating that even our most sophisticated creations could be healed through human courage and expertise. The mission itself unfolded like a carefully choreographed dance performed in the most unforgiving theatre imaginable. On December 2nd, 1993, Endeavour's robotic arm reached out and gently captured Hubble, drawing the telescope into the shuttle's cargo bay with the delicacy of cradling a sleeping child. For the next 5 days, the cargo bay would become an operating room unlike any other, where astronauts would perform microsurgery on humanity's most important scientific instrument. The first spacewalk began before dawn on December 4th, with astronauts Story Musgrave and Jeff Hoffman floating out into the cargo bay to begin the most complex repair job ever attempted in space. Their first task was to replace Hubble's faulty solar arrays, which had been vibrating and causing pointing problems for the telescope. Working with tools specially designed for use in bulky spacesuits, they carefully removed the old arrays and installed new ones that would provide steady, reliable power for years to come. Watching the astronauts work was like observing a slow-motion ballet performed against the backdrop of infinity. Every movement was deliberate, every action planned and rehearsed. They communicated in the calm, professional tones of people who understood that precision and patience were their greatest tools in the hostile environment of space. When they encountered unexpected problems, and they did, as they always do in complex operations, They solved them with the kind of methodical creativity that comes from years of training and an absolute commitment to success. The second spacewalk, performed by Musgrave and Swiss astronaut Claude Nicollier, focused on installing the new wide-field and planetary camera. The WFPC-2 was about the size of a baby grand piano and weighed nearly 620 pounds, manageable in the weightlessness of space, but requiring extreme care to position correctly within Hubble's instrument bay. The installation required connecting dozens of electrical and data cables, each one crucial to the camera's operation. The third and fourth spacewalks tackled the installation of COSTAR, the corrective optics package that would restore clear vision to Hubble's other instruments. COSTAR was a marvel of engineering miniaturization, containing 10 small mirrors that would intercept Hubble's scattered light and redirect it with nanometer precision. Installing it required removing one of Hubble's existing instruments and carefully positioning the COSTAR unit in its place, aligning the optical components with tolerances measured in fractions of the wavelength of light. Perhaps the most challenging aspect of the repair was the installation of new gyroscopes and other pointing system components. These devices would allow Hubble to aim at astronomical targets with unprecedented precision, holding its gaze steady for hours at a time while gathering the faint light of distant galaxies. The gyroscopes had to be installed deep within Hubble's structure, requiring astronauts to work in confined spaces while wearing suits that limited their mobility and dexterity. The fifth and final spacewalk addressed the remaining technical issues and performed final checks on all the new systems. By the time Musgrave and Hoffman completed their work, they had spent more than 35 hours outside the shuttle, making this one of the longest and most complex series of spacewalks ever performed. Every component had been installed according to specifications that demanded perfection, because there would be no opportunity for minor adjustments once Hubble was released back into its solitary orbit. The moment of truth came on December 10th, when Endeavour's robotic arm gently released Hubble back into space. The telescope looked different now, sporting new solar arrays and carrying within its structure the optical corrections that would hopefully transform it from an expensive disappointment into the revolutionary instrument it had been designed to be. As Endeavour slowly backed away, Hubble began its careful process of reactivation, systematically bringing its systems back online after the most extensive maintenance ever performed on a spacecraft. The weeks that followed were filled with the kind of tense anticipation that comes when years of work and billions of dollars hang in the balance. Engineers activated Hubble's systems one by one, carefully checking each component to ensure that the repairs had been successful. The new solar arrays deployed properly, providing steady power without the vibrations that had plagued the original arrays. The new gyroscopes came online, allowing Hubble to point with the rock-steady precision that precision astronomy required. But the real test would come with the first light from the repaired telescope. On January 13th, 1994, Hubble pointed its newly corrected vision toward a star and captured an image that would change everything. The photograph that arrived at the Space Telescope Science Institute was perfect, crisp, clear, showing stars as precise points of light, without the halos and scattered light that had marked Hubble's earlier images. The transformation was so complete, so dramatic, that many astronomers who first saw the corrected images simply couldn't believe what they were seeing. The same telescope that had been the subject of ridicule and disappointment just months earlier was now producing images of unprecedented clarity and beauty. The repair had worked perfectly, restoring not just Hubble's vision, but also faith in humanity's ability to achieve seemingly impossible goals through courage, skill, and determination. the success of servicing. Mission 1 did more than fix a broken telescope. It established a new paradigm for space-based astronomy. Hubble became the first space telescope designed for regular maintenance and upgrades, creating opportunities for continuous improvement that would keep it at the forefront of astronomical research for decades. 4 more servicing missions would follow, each one extending Hubble's capabilities and operational lifetime far beyond what anyone had originally thought possible. The cultural impact of the successful repair was profound. The astronauts who had performed the mission became heroes not just within NASA, but in the broader public imagination. They had demonstrated that human ingenuity and determination could overcome even the most daunting technical challenges, transforming failure into success, triumph through skill, courage, and an absolute refusal to accept defeat. More importantly, the repair mission transformed Hubble from a symbol of technological hubris into an icon of human resilience and achievement. The telescope that had once been mocked as a $1.5 billion blunder became a beloved symbol of scientific discovery and human capability. Its story became a parable about the importance of persistence, the value of taking risks in pursuit of great goals, and the remarkable things that become possible when talented people refuse to give up on their dreams. As Hubble resumed its patient orbit around Earth with perfect vision restored, it carried with it not just the ability to see the universe with unprecedented clarity, but also a profound message about the human spirit. Sometimes our greatest triumphs emerge not from flawless execution, but from our capacity to face our failures directly, learn from our mistakes, and find ways to transform disappointment into something even more beautiful than we originally dared to imagine. Imagine holding in your hands a photograph that shows you the exact moment when the universe was young. Not a painting or an artist's conception, but an actual image of galaxies as they appeared when the cosmos was less than 1 billion years old, their light having travelled across space for over 13 billion years to reach Hubble's perfect mirror. This is what astronomers found themselves contemplating in the years following Hubble's successful repair, as the telescope began sending back images and data that would fundamentally reshape our understanding of the universe we inhabit. With its vision fully restored, Hubble became humanity's time machine, capable of looking so far into space that it was literally seeing backward through cosmic history. Every distant galaxy captured in its images appeared as it was millions or billions of years ago, when the light now reaching Earth first began its long journey across the expanding universe. The deeper Hubble looked into space, the further back in time it could see, until it was observing epochs when the universe was fundamentally different from the cosmos we know today. One of Hubble's most profound contributions came through its patient measurement of a cosmic phenomenon that would challenge everything astronomers thought they knew about the universe's fate. Edwin Hubble, the astronomer for whom the telescope was named, had discovered in the 1920s that the universe was expanding. Galaxies were moving away from us, and the more distant they were, the faster they appeared to be receding. This relationship, known as the Hubble constant, provided a way to measure the universe's age and predict its future. But the space telescope that bore Hubble's name would discover something that Edwin Hubble himself never could have imagined. By observing distant supernovae, exploding stars that serve as cosmic lighthouses, visible across billions of light years, Hubble helped reveal that the expansion of the universe was not slowing down as everyone expected, but actually accelerating. Something was pushing galaxies apart with ever-increasing force, something invisible and mysterious that astronomers would come to call dark energy. The discovery emerged slowly like a photograph developing in a dark room, astronomers used Hubble to study Type Ia supernovae, stellar explosions so consistent in their brightness that they could serve as standard candles for measuring cosmic distances. By comparing how bright these supernovae appeared to be with how bright they should have been based on their distance, researchers could determine whether the universe's expansion was speeding up or slowing down. What they found was completely unexpected. The distant supernovae appeared dimmer than they should have, meaning they were farther away than predicted by models of a decelerating universe. The only explanation was that the expansion of space itself was accelerating, driven by some mysterious force that comprised roughly 70% of the universe's total energy content. This dark energy was invisible, detectable only through its gravitational effects on the large-scale structure of the cosmos. The implications were staggering. If dark energy continued to dominate the universe's evolution, the cosmos would expand forever, with galaxies eventually moving so far apart that future astronomers would see only empty darkness beyond their own galaxy. The universe that seemed so rich and full of stars when viewed through Hubble's eyes was actually dominated by something completely mysterious. Something that left no direct trace except its inexorable push against the fabric of space and time itself. Hubble's deep field observations provided another kind of cosmic revelation, this one visual and immediate in its impact. In 1995, astronomers pointed the telescope at what appeared to be an empty patch of sky in the constellation Ursa Major, no bigger than a grain of sand held at arm's length. They left Hubble's camera open for 10 days, gathering every photon of light that fell on its detectors during that time, building up an image from the faintest whispers of electromagnetic radiation. The resulting photograph, known as the Hubble Deep Field, revealed a universe far more crowded and active than anyone had imagined. That tiny, apparently empty region of sky contained nearly 3,000 galaxies, each one a collection of billions of stars, many appearing as they were when the universe was only a fraction of its current age. The image was like looking through a keyhole and discovering that the room beyond was filled with entire worlds, each one unique, each one telling its own story of cosmic evolution. The galaxies in the deep field appeared in every stage of development, from mature spiral and elliptical systems that looked much like our own Milky Way, to strange, irregular objects that seemed to be caught in the act of formation. Some showed the blue glow of vigorous star formation, where new suns were being born at rates hundreds of times faster than in today's galaxies. Others displayed the red colours of ancient stellar populations, suggesting they had exhausted their star-forming fuel billions of years ago. What made the deep field images particularly profound was their implication for the universe's overall population. If a tiny, randomly selected patch of sky contained thousands of galaxies, then the observable universe must contain hundreds of billions of galaxies, each one potentially harbouring planets, perhaps even life. The cosmic census revealed by Hubble suggested that our universe was not just vast, but almost unimaginably rich in worlds and possibilities. Hubble's exploration of our own solar system revealed wonders closer to home that were no less remarkable than its deep space discoveries. When comet Shoemaker-Levy 9 broke apart and crashed into Jupiter in 1994, Hubble provided the most detailed observations ever made of such a cosmic collision. The telescope watched as fragments of the comet, each one several kilometers across, slammed into Jupiter's atmosphere at speeds of 60 kilometers per second, creating explosions that were visible even through amateur telescopes on Earth. The impact observations revealed the dynamic nature of our solar system, showing how gravitational interactions between planets and smaller bodies continue to shape the cosmic neighborhood we inhabit. The scars left on Jupiter's atmosphere by the comet impacts were larger than Earth itself, demonstrating the incredible energies involved in cosmic collisions and reminding us that our solar system remains an active, evolving environment even after 4.6 billion years. Perhaps even more intriguing were Hubble's discoveries around Pluto, then still considered the ninth planet in our solar system. The telescope's sharp vision allowed astronomers to measure Pluto's size and mass with unprecedented accuracy, revealing that it was much smaller than previously thought. More surprisingly, Hubble discovered that Pluto had at least 4 moons in addition to Charon, the large satellite that had been known since 1978. These discoveries around Pluto helped reshape our understanding of the outer solar system, revealing it to be populated by numerous small, icy worlds left over from the solar system's formation. Hubble's observations contributed to the reclassification of Pluto as a dwarf planet, not because it had become less interesting, but because it was revealed to be the brightest member of a whole new class of solar system objects. The telescope's studies of stellar evolution provided another window into cosmic processes that operate on timescales far longer than human civilizations. Hubble observed stars in every stage of their life cycles, from the stellar nurseries where new suns are born within clouds of gas and dust, to the spectacular death throes of massive stars as they explode as supernovae, scattering the elements necessary for life across the cosmos. One of the most visually stunning examples of stellar evolution captured by Hubble was the Crab Nebula, the expanding remnant of a supernova that Chinese astronomers observed in 1054 AD. Hubble's images showed the nebula's intricate structure in unprecedented detail, revealing how the explosion had created a complex web of filaments and shock waves still expanding outward nearly 1,000 years later. At the center of this cosmic artwork lay a pulsar, a neutron star spinning 30 times per second, the compressed core of the original star now containing the mass of our Sun in an object only 20 kilometers across. These stellar observations weren't just beautiful, they revealed the cosmic recycling process that makes planets and life possible. The heavy elements that make up rocky planets like Earth and the complex chemistry that underlies biology are forged in the nuclear furnaces of massive stars and dispersed throughout the galaxy when those stars explode. Hubble's images of stellar nurseries showed this process in action, as shock waves from ancient supernovae triggered the collapse of gas clouds, leading to the formation of new stars and planetary systems enriched with the elements created by previous generations of stellar evolution. The telescope also revolutionized our understanding of black holes, those enigmatic objects where gravity becomes so strong that not even light can escape. While black holes themselves are invisible, Hubble could observe the effects of their intense gravitational fields on surrounding matter. The telescope discovered supermassive black holes at the centers of galaxies, some containing billions of times the mass of our Sun, surrounded by swirling disks of superheated gas that glow brightly as they spiral inward toward the point of no return. Perhaps most remarkably, Hubble revealed that these supermassive black holes weren't cosmic accidents, but integral parts of galaxy formation and evolution. The telescope's observations showed a close relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, suggesting that galaxies and their black holes grow together through processes that astronomers are still working to understand. The study of exoplanets, worlds orbiting other stars, became another frontier where Hubble made groundbreaking contributions. While the telescope wasn't designed to discover exoplanets directly, it could study their atmospheres by observing how starlight changed as planets passed in front of their parent stars. These transit observations allowed astronomers to determine not just the size and orbital characteristics of distant worlds, but also the composition of their atmospheres. Hubble's atmospheric studies of exoplanets revealed worlds unlike anything in our solar system. Some planets had atmospheres rich in water vapor, suggesting the possibility of clouds and weather systems on distant worlds. Others showed evidence of exotic chemistry, with clouds made of silicate particles or atmospheres stripped away by the intense radiation of their parent stars. Each atmospheric analysis added to our understanding of how planetary systems form and evolve, providing crucial context for understanding our own cosmic neighborhood. The cultural impact of these discoveries extended far beyond the astronomical community. Hubble's images of distant galaxies, stellar nurseries, and cosmic phenomena became part of the shared visual vocabulary of our species, appearing in textbooks, museums, documentaries, and art installations around the world. The telescope had transformed abstract astronomical concepts into tangible, beautiful images that anyone could appreciate and wonder at. More profoundly, Hubble's revelations about dark energy, the abundance of galaxies, and the processes of stellar and planetary formation had begun to reshape humanity's understanding of our place in the cosmos. The universe revealed by the telescope was far stranger and more magnificent than anyone had imagined, a cosmos dominated by invisible forces, populated by billions upon billions of galaxies, and governed by processes that created both the elements necessary for life and the spectacular cosmic environments where that life might take root. As Hubble continued its patient observations, each new discovery added another piece to the vast puzzle of cosmic evolution, revealing a universe that was simultaneously more alien and more wondrous than our ancestors could ever have conceived. The telescope that had been rescued from failure had become humanity's guide to understanding the deepest mysteries of existence itself, transforming our species from inhabitants of a small world into conscious participants in a cosmic story of almost unimaginable scope and beauty. Picture yourself standing in a dark room in the 1990s, watching as an image slowly emerges from the chemical bath, but instead of a family portrait or landscape photograph, what appears before your eyes is a cosmic cathedral made of gas and starlight, towering pillars of creation stretching across light years of space, backlit by the fires of newborn stars. This is how astronomers first witnessed the transformation of raw Hubble data into the images that would change not just science, but the way our entire species sees itself in the universe. The process of turning Hubble's digital observations into the breathtaking images that captured the world's imagination was itself a kind of alchemy, blending rigorous science with artistic sensibility in ways that had never been attempted before. Each photograph that emerged from the Space Telescope Science Institute was the result of careful choices made by a team of image processors who understood that they were not just creating scientific documentation, but crafting humanity's first clear portraits of the cosmos. The raw data that Hubble sends to Earth tells its story in numbers. Streams of digital information describing the brightness of pixels across different wavelengths of light. These numbers are scientifically precise, but they're not immediately meaningful to human eyes accustomed to seeing the world in visible light. Most of Hubble's observations capture wavelengths that our eyes cannot detect: ultraviolet radiation from hot young stars, infrared light from cool dust clouds, emission lines from exotic gases excited by stellar radiation. Transforming this invisible information into visible beauty requires what image processors call false color mapping, a technique where different wavelengths of light are assigned colors that allow human eyes to see structures and processes that would otherwise remain hidden. The choice of which colors to assign to which wavelengths is both scientific and aesthetic, guided by the need to reveal important astronomical features while creating images that convey the wonder and majesty of the cosmic phenomena they represent. The Hubble Heritage Project, established to create public release versions of the telescope's most spectacular observations, became a bridge between the technical world of professional astronomy and the broader human desire to see and understand our place in the universe. The team responsible for these images worked like Renaissance artists, using the latest digital technology to reveal the hidden beauty in datasets that might otherwise remain accessible only to specialists. Consider the creation of one of Hubble's most famous images, the Pillars of Creation in the Eagle Nebula. The raw observations showed 3 distinct wavelengths of light: hydrogen emissions that revealed the structure of the gas pillars, doubly ionized oxygen that highlighted the edges where stellar winds were sculpting the nebula, and singly ionized sulfur that traced the distribution of different chemical elements. The image processors mapped these wavelengths to red, green, and blue respectively, creating a photograph that was both scientifically accurate and visually stunning. The resulting image became one of the most recognizable photographs in human history, rivaling the most famous earthly landmarks in its cultural impact. The towering columns of gas and dust, sculpted by stellar winds into shapes that seemed almost architectural in their grandeur, spoke to something deep in human consciousness. Here was proof that the universe was not just vast and empty, but rich with structure and beauty on scales that challenged imagination. But the scientific accuracy of these images required constant vigilance against the temptation to prioritize visual appeal over astronomical truth. Each processing decision needed to preserve the data's scientific integrity while making it accessible to human perception. Colors were chosen to highlight real physical processes: the blue glow of hot young stars, the red emission of hydrogen gas, the golden hues of dust clouds warmed by stellar radiation. The goal was never to create pretty pictures, but to reveal the actual beauty that existed in cosmic phenomena when viewed with eyes more sensitive than human vision. The technical challenges of creating these images were formidable. Hubble's detectors could capture incredible detail, but they could only observe small portions of the sky at a time. Creating wide-field mosaics required combining dozens of individual observations, each one precisely aligned to create seamless panoramas of cosmic landscapes. The process was like assembling a jigsaw puzzle where each piece had to be color-corrected, contrast-adjusted, and geometrically aligned with its neighbors. Some of Hubble's most stunning images required months of observation time spread across multiple years. The Hubble Ultra Deep Field, which revealed galaxies as they appeared when the universe was less than 1 billion years old, was created from 800 separate exposures taken over the course of 4 months. The final image represented 11.3 days of total exposure time, gathering photons that had been traveling through space for over 13 billion years. The democratization of cosmic beauty through Hubble's public image releases fundamentally changed the relationship between professional astronomy and popular culture. Before Hubble, astronomical images were primarily scientific tools, published in specialized journals and accessible mainly to researchers. Hubble's photographs became genuine works of art, displayed in galleries and museums, featured on magazine covers, and shared through the emerging internet as humanity's first viral space content. The cultural impact went far beyond visual appreciation. These images provided concrete evidence for abstract astronomical concepts. that had previously existed only as theoretical models and mathematical equations. When people could see actual photographs of galaxies colliding, stars being born in nebular nurseries, or planetary nebulae expanding from dying stars, cosmic evolution transformed from academic theory into visceral reality. Children growing up in the Hubble era were the first generation in human history to have detailed, beautiful images of the universe as a normal part of their visual environment. Classroom walls displayed Hubble photographs alongside maps of the world and portraits of historical figures. Computer screensavers cycled through cosmic imagery that previous generations could never have imagined. The universe became familiar in ways that fundamentally altered how young minds conceived of humanity's place in the cosmos. The intersection of Hubble imagery with digital technology created new forms of public engagement with science. As personal computers became common household items, Hubble images became some of the most popular downloads on the early internet. Websites dedicated to space photography attracted millions of visitors, making astronomical imagery as accessible as family photos. The rise of social media platforms provided new venues for sharing cosmic wonder, with Hubble images becoming some of the most widely circulated content in the digital age. Professional artists began incorporating Hubble imagery into their work, creating hybrid pieces that blended scientific observation with human interpretation. Musicians composed symphonies inspired by the rhythm of pulsar signals detected by Hubble's observations. Poets wrote verses that attempted to capture in words the sublime experience of seeing galaxies in collision or witnessing the death of stars. The telescope had become a muse for creative expression across multiple disciplines. The religious and spiritual responses to Hubble imagery were equally profound. The photographs seemed to provide visual evidence for concepts that had previously existed only in theological speculation: infinity made visible, creation stories rendered in actual starlight, the sublime beauty of cosmic order. Many people found in Hubble's images a new vocabulary for expressing their sense of wonder at the universe's magnificent scale and intricate organization. However, this popularization of cosmic imagery also created new challenges for science communication. The enhanced and color-processed nature of many Hubble images sometimes led to misconceptions about what the universe actually looks like to the human eye. Educational efforts were needed to help the public understand that, while the structures and phenomena shown in Hubble images were real, the colors and enhancements were often chosen to reveal details that would otherwise remain invisible. The archive of Hubble observations became one of humanity's most valuable cultural and scientific resources. Decades of data were preserved and made publicly available, allowing researchers around the world to make new discoveries using observations that might be years or decades old. The democratization of access to Hubble data enabled citizen scientists to contribute to professional research, analyzing images and identifying phenomena that automated systems might have missed. Museums and planetariums transformed their exhibits to showcase Hubble discoveries, using the telescope's images to create immersive experiences that allowed visitors to journey virtually through cosmic landscapes. The National Air and Space Museum, the Hayden Planetarium, and similar institutions around the world became temples to the new cosmic perspective that Hubble had made possible, places where people could gather to contemplate their place in a universe far grander and more beautiful than previous generations had dared to imagine. The educational impact extended beyond formal institutions into homes and communities worldwide. Parents could show their children photographs of actual stellar nurseries and explain how the elements in their bodies were forged in the hearts of ancient stars. Teachers could use Hubble images to make abstract concepts concrete, showing students the actual effects of gravity on galactic structure or the real consequences of stellar evolution. Perhaps most significantly, Hubble's images contributed to a fundamental shift in human perspective that philosophers and theologians are still working to understand. For the first time in our species' history, we could see ourselves not just as inhabitants of Earth, but as participants in a cosmic story of breathtaking scale and complexity. The photographs showed us that we live in a universe where beauty and wonder exist on every scale, from the intricate structure of planetary nebulae to the vast web of galaxies that stretches across billions of light years. The cultural revolution that Hubble sparked was not just about pretty pictures or popular science. It was about expanding human consciousness to encompass the true scale and beauty of the universe we inhabit. The telescope had become more than a scientific instrument. It was a window through which our entire species could glimpse the sublime architecture of creation itself. This transformation from scientific tool to cultural icon represented something unprecedented in human history. The first time that detailed, beautiful images of distant cosmic phenomena became part of the shared visual vocabulary of our species. Children who grew up with Hubble imagery would carry with them throughout their lives a sense of the universe's vastness and beauty that no previous generation had possessed, fundamentally altering humanity's understanding of home, wonder, and our place among the stars. Picture a child sitting in their bedroom in 1995, carefully peeling a Hubble photograph from the pages of National Geographic and taping it to their wall next to a poster of their favourite movie star. The image shows towering pillars of gas and dust, sculpted by stellar winds into cathedral-like spires, backlit by the fires of newborn stars. That child falls asleep each night, looking up at a universe that no human generation before them had ever seen, their dreams filled with cosmic landscapes that were becoming as familiar as earthly mountains and rivers. This quiet revolution in human consciousness was perhaps Hubble's most profound achievement. Not any single discovery, but the gradual transformation of how our entire species sees itself in relation to the cosmos. For the first time in human history, detailed images of distant galaxies, stellar nurseries, and cosmic phenomena became part of the everyday visual environment in which children grew up. The universe was no longer an abstract concept discussed in science classes, but a tangible, beautiful reality that anyone could explore simply by looking at a computer screen or opening a magazine. The change happened so gradually that many people didn't notice it occurring. One day, cosmic imagery was rare and precious, available only to professional astronomers and the occasional science documentary. The next, it seemed, images of spiral galaxies and colourful nebulae were everywhere, on websites, in coffee shops, as screensavers on office computers, printed on t-shirts and coffee mugs. The sublime had become commonplace, and in becoming commonplace, it had quietly revolutionized human imagination. Consider what this meant for the astronomers who had spent their careers studying the universe through ground-based telescopes, forever frustrated by the atmospheric turbulence that blurred their observations. Suddenly, they had access to images so sharp and detailed that they could spend hours exploring a single photograph, discovering new structures and phenomena in familiar objects. Galaxies that had appeared as fuzzy smudges in even the largest terrestrial telescopes revealed intricate spiral arms, dust lanes, and star formation regions, with a clarity that made them seem almost close enough to touch. The psychological impact on the scientific community was profound. Researchers who had devoted decades to studying theoretical models and indirect observations could suddenly see the actual objects of their research displayed in breathtaking detail. It was like spending years reading descriptions of a beautiful landscape, only to suddenly find yourself standing in the middle of it, able to see every tree, every rock, every play of light and shadow with perfect clarity. But perhaps more importantly, Hubble democratized wonder. Before the Space Telescope, astronomical imagery was primarily the domain of specialists, researchers who understood how to interpret photographic plates and extract scientific information from grainy, low-contrast images. Hubble's photographs needed no interpretation to inspire awe. A child could look at an image of the Cat's Eye Nebula or the Whirlpool Galaxy and immediately understand that they were seeing something magnificent, even if they couldn't explain the physics behind what they were observing. This accessibility transformed astronomy from a highly technical field that seemed remote from everyday life into something that could touch anyone's sense of wonder and curiosity. Parents found themselves looking up at the night sky with their children, pointing out constellations while talking about the galaxies that Hubble had revealed beyond the stars visible to the naked eye. The universe had become a shared cultural reference point, a common vocabulary of beauty and mystery that transcended educational backgrounds and cultural boundaries. The Internet's emergence during Hubble's operational lifetime created unprecedented opportunities for sharing cosmic imagery. Websites dedicated to space photography attracted millions of visitors who would browse through galleries of nebulae, galaxies, and stellar phenomena with the same casual interest they might show for vacation photographs or family snapshots. The universe had become browsable, searchable, shareable, a vast collection of cosmic postcards available to anyone with an internet connection. This digital revolution in science communication happened to coincide perfectly with Hubble's productive years, creating a feedback loop where public interest in space imagery drove demand for more and better cosmic photographs, while the availability of stunning images through digital channels created new audiences hungry for astronomical discoveries. Social media platforms became venues for sharing cosmic wonder, with Hubble images regularly becoming some of the most widely circulated content across all forms of digital media. The transformation wasn't limited to casual appreciation of cosmic beauty. Hubble's images began appearing in unexpected contexts: art galleries, fashion designs, architectural projects, music videos. The boundary between scientific imagery and artistic expression became increasingly blurred as creative professionals found inspiration in the colors, shapes, and compositions revealed by the Space Telescope. Designers discovered that the universe was filled with patterns and color schemes that could inspire everything from fabric designs to building facades. Musicians found rhythms in the data streams from pulsating stars. Composers created symphonies inspired by the expansion of supernova remnants, and poets struggled to find words that could capture the emotional impact of seeing billions of galaxies scattered across space like seeds in a cosmic garden. The telescope had become a muse for creative expression across every imaginable medium, inspiring works that blended scientific accuracy with human emotion in ways that neither art nor science could achieve alone. Religious and spiritual communities found themselves grappling with images that seemed to provide visual evidence for concepts that had previously existed only in theological speculation. The photographs of cosmic creation, stellar nurseries where new suns were being born from clouds of gas and dust, resonated with creation narratives from cultures around the world. The images of dying stars casting off shells of glowing gas suggested themes of transformation and renewal that spoke to deep human intuitions about the cyclical nature of existence. Different faith traditions found different meanings in Hubble's revelations. Some saw evidence of divine craftsmanship in the intricate structures revealed by the telescope. Others found confirmation of ancient teachings about the interconnectedness of all things, as Hubble showed how the heavy elements created in stellar cores were scattered throughout space to become part of new stars, planets, and potentially life itself. The images provided a visual vocabulary for discussing humanity's place in a cosmos far grander and more beautiful than earlier generations could have imagined. The educational impact rippled outward from formal institutions into homes, communities, and casual conversations. Parents who had struggled to answer their children's questions about the universe suddenly had access to actual photographs that could illustrate concepts like stellar evolution, galactic structure, and the expansion of space. Teachers discovered that students who might struggle with abstract mathematical concepts could grasp astronomical ideas when they could see the actual objects being discussed. But the transformation went deeper than simply having better visual aids for science education. The availability of Hubble imagery changed the very questions that children asked about the universe. Instead of wondering whether other worlds existed, they wanted to know what those worlds might look like. Rather than asking if stars were born and died, they were curious about the specific processes by which stellar nurseries created new suns. The telescope had transformed cosmic speculation into cosmic exploration, even for the youngest minds. Libraries became informal planetariums as children and adults alike browsed through books filled with Hubble photographs. The science sections, once the domain of serious students and dedicated hobbyists, attracted casual browsers who simply wanted to spend time looking at beautiful images of the cosmos. Librarians reported that astronomy books were among the most frequently checked out materials, with readers returning again and again to spend quiet time contemplating images that seemed to reveal new details with each viewing. Coffee shops and bookstores began displaying cosmic calendars and poster books featuring Hubble imagery, turning everyday commercial spaces into galleries for contemplating the universe. People would pause in their daily routines to study photographs of distant galaxies while waiting for their morning coffee, incorporating moments of cosmic wonder into the rhythm of ordinary life. The sublime had become accessible in the most mundane settings, available to anyone who chose to notice it. The generation of children who grew up with Hubble imagery as part of their normal visual environment developed a different relationship with the cosmos than any previous generation had possessed. For them, the universe wasn't a distant, abstract concept, but a familiar neighborhood filled with recognizable landmarks. They could identify the Orion Nebula as easily as they could point out their hometown on a map, and they understood intuitively that Earth was part of the universe of a much larger community of worlds scattered throughout space. These young people reached adulthood with an intuitive understanding of cosmic scale that previous generations had acquired only through years of specialized study. They thought naturally in terms of light years and billions of years, not because they had been trained to do so, but because these concepts had been part of their visual environment from childhood. They possessed what might be called cosmic literacy, the ability to read and interpret the visual language of astronomical phenomena with the same ease that their parents might read a newspaper or understand a weather map. The psychological research that emerged around this generational shift revealed fascinating differences in how people who grew up with Hubble imagery conceived of humanity's place in the universe. Surveys showed that younger people were more likely to think of Earth as one planet among many, less likely to view humanity as uniquely special in a cosmic sense, and more inclined to consider the possibility of life elsewhere in the universe. These weren't necessarily better or worse perspectives, than those held by earlier generations, but they represented a fundamental shift in human consciousness that was directly attributable to Hubble's influence. Art therapists and counselors began incorporating cosmic imagery into their practice, finding that Hubble photographs could serve as powerful tools for helping people gain perspective on their personal struggles. The images seemed to offer a kind of visual meditation on the themes of scale, beauty, and humanity's place in larger patterns of meaning. Patients reported that contemplating photographs of distant galaxies helped them feel simultaneously humble and connected, small in cosmic terms, but part of something magnificent and ongoing. This cosmic perspective had practical consequences that extended far beyond astronomy. Environmental movements found in Hubble's images powerful illustrations of Earth's uniqueness and fragility. The photographs of distant galaxies and sterile cosmic landscapes made our planet's abundance of life seem both precious and improbable, worthy of protection and careful stewardship. The overview effect that astronauts had described, seeing Earth as a unified, fragile system suspended in space, became accessible to anyone who could contemplate Hubble's images of the cosmic context in which our world exists. International cooperation in space exploration received a boost from Hubble's universal appeal. The telescope's discoveries belonged to no single nation or culture, but represented the shared heritage of our entire species. Scientists from countries with strained political relationships found common ground in their shared fascination with cosmic phenomena that knew no earthly boundaries. Hubble became a symbol of what human cooperation could achieve when directed toward peaceful goals that inspired rather than divided. The long-term psychological effects of living in a universe revealed by Hubble are still unfolding as the first generation to grow up with space telescope imagery reaches adulthood. These individuals carry with them an intuitive understanding of cosmic scale and complexity that previous generations acquired only through years of specialized education. They think naturally in terms of deep time, vast distances, and the interconnected processes that link stellar evolution to the chemistry of life. As Hubble continued its patient observations year after year, its role evolved from revolutionary discoverer to trusted cosmic correspondent, sending back regular reports from the universe that had become as familiar and expected as weather forecasts or news updates. The telescope had transformed from a remarkable scientific instrument into an integral part of human culture, a mechanical ambassador that had fundamentally altered our species' understanding of home, wonder, and our place among the infinite mysteries that surround our small world. The child who fell asleep looking at Hubble images on their bedroom wall grew up in a universe that previous generations could never have imagined, not because the cosmos had changed, but because humanity had developed the eyes necessary to see it clearly at last. And in seeing it clearly, we had discovered that the universe was not just vast and ancient, but beautiful beyond our wildest dreams, filled with wonders that continued to unfold with each new observation, each new discovery, each new image that added another verse to the ongoing poem of cosmic exploration. Picture yourself standing in your backyard on a clear night 30 years from now, pointing up at a particular star and telling your grandchild, "That's where Hubble used to be." By then, the telescope will be nothing more than a memory preserved in photographs and data archives, but the child looking up with you will inhabit a universe that Hubble revealed, a cosmos filled with billions of galaxies, where planets dance around distant suns, where stars are born in pillars of creation and die in spectacular explosions that seed space with the elements of life itself. There's something almost magical about this inheritance we're leaving to future generations. Children born today will grow up in a world where the universe is no longer mysterious and empty, but rich with detail and wonder. They'll know, as naturally as they know their own address, that we live in a galaxy called the Milky Way, that it contains hundreds of billions of stars, and that it's just one galaxy among trillions scattered across an expanding cosmos. This knowledge, which previous generations could only dream about, will be as familiar to them as the color of the sky. Tonight, as Hubble continues its patient orbit 350 miles above your head, it carries with it more than just sophisticated instruments and carefully planned observations. It carries the dreams of everyone who ever looked up at the stars and wondered what secrets they might hold. The telescope has become humanity's most successful ambassador to the cosmos, our mechanical representative in the realm of infinite darkness, sending back postcards from the edge of space and time. But Hubble is aging, and like all of us, it won't last forever. Its gyroscopes, which once spun with perfect precision, sometimes wobble now like old bicycle wheels. Its solar panels, battered by decades of unfiltered sunlight and microscopic meteorites, generate a little less power each year. The instruments that once represented the pinnacle of human technology now seem quaint compared to the capabilities of newer telescopes being built and planned. Yet there's something deeply moving about Hubble's graceful approach to the end of its remarkable journey. The telescope continues working with the quiet dignity of an elderly craftsperson who still takes pride in their work despite the tremor in their hands. Every image it captures now feels precious, a gift from a faithful friend who has shared more wonders with us than we ever dared to hope for when we first released it into the cosmic dark. The James Webb Space Telescope, with its golden mirror and infrared vision, now peers even deeper into space than Hubble ever could. Webb can see the very first galaxies that formed after the Big Bang, cosmic infants appearing as they were when the universe was barely out of its cradle. It's a magnificent instrument that honors Hubble's legacy by pushing the boundaries of cosmic exploration even further into the unknown. But Webb doesn't replace Hubble any more than a grandchild replaces a grandparent. They see the universe differently, each revealing aspects of cosmic beauty that remain invisible to the other. Hubble shows us the cosmos in colors our eyes might recognize if we could somehow travel to distant star-forming regions or witness the collision of galaxies firsthand. Webb reveals hidden structures in infrared light, the warm glow of dust clouds and the heat signatures of planets orbiting distant suns. Together, they demonstrate something profound about the nature of discovery itself. Each new way of seeing adds layers to our understanding, rather than erasing what came before. The universe revealed by radio telescopes is different from the one shown by X-ray observatories, which differs again from the cosmos visible in gamma rays or gravitational waves. Each perspective is true, each is beautiful, and each contributes to a growing portrait of reality that no single instrument could capture alone. There's poetry in this multiplication of cosmic perspectives. We've learned to see the universe through many different kinds of eyes, some sensitive to the heat of distant worlds, others tuned to the radio whispers of spinning neutron stars, still others capable of detecting the ripples in space-time itself, caused by colliding black holes billions of years ago. Hubble taught us that clear vision was possible. Its successors are showing us just how many different kinds of clarity the cosmos offers to those patient enough to look. The children who are growing up with Webb's infrared revelations will inhabit an even richer universe than those who came of age with Hubble's visible light portraits. They'll understand intuitively that planets form in disks of dust around young stars, that galaxies grow through mergers and collisions across cosmic time, that the elements in their bodies were forged in stellar furnaces and scattered through space by dying stars. This cosmic perspective will shape how they think about everything from their place in nature to their responsibilities to future generations. But Hubble's influence extends far beyond the realm of astronomy and science education. The telescope has taught us something important about the rewards of thinking in the long term, of building things designed to last, of maintaining and improving rather than discarding and replacing. In our throwaway culture of planned obsolescence and rapid technological turnover, Hubble represents a different philosophy, one that values durability, maintainability, and the patient accumulation of knowledge over time. The 5 servicing missions that kept Hubble operating far beyond its planned lifetime demonstrated something remarkable about human ingenuity and dedication. Astronauts risked their lives to repair and upgrade a telescope that many considered obsolete, not because it was economically sensible, but because they understood that some things are worth preserving. They showed us that even our most sophisticated creations can be maintained and improved if we're willing to invest the effort and resources required. This lesson resonates far beyond space exploration. In an age when we're grappling with climate change, resource depletion, and the sustainability of human civilization, Hubble's story offers hope. It shows us that careful maintenance, thoughtful upgrades, and long-term thinking can extend the useful life of complex systems far beyond what their original designers imagined. The telescope that was supposed to operate for 15 years has given us more than 3 decades of discovery, demonstrating the rewards of refusing to accept artificial limits on what's possible. The thousands of scientists, engineers, technicians, and administrators who have worked on Hubble over the decades represent a community united by shared purpose and mutual dedication. They've shown us what human cooperation can accomplish when it's directed toward goals that inspire rather than divide. The telescope belongs to no single nation or institution, but to our entire species. A gift from the portion of humanity that chose to reach toward the stars to the portion that dreams of understanding our place among them. As we look toward Hubble's eventual end, there's comfort in knowing that its most important discoveries have become part of the permanent heritage of human knowledge. The images it captured, the data it collected, and the questions it answered will continue to inspire and inform long after the telescope itself has returned to Earth as a streak of light across the night sky. Future archaeologists studying our civilization might wonder why we invested so much effort in building machines to look at distant stars when there were so many problems to solve here on Earth. But perhaps they'll understand that Hubble represented something essential about human nature. Our need to explore, to question, to seek beauty and meaning in the vastness that surrounds our small world. The telescope embodied our species' finest qualities: curiosity, persistence, creativity, and the ability to work together toward goals that transcend individual ambition. In those final moments, when Hubble's orbit decays enough for it to begin its fiery descent through Earth's atmosphere, the telescope will complete a journey that began not with its launch in 1990, but with the first human who looked up at the stars and wondered what they were. The light from its burning will add one final photon to the cosmic collection of electromagnetic radiation that fills the universe, a fitting end for an instrument that spent its life gathering ancient light from the most distant corners of space and time. But the story doesn't end there. Somewhere in a classroom, a child is looking at a Hubble image for the first time, gasping with wonder at the sight of galaxies colliding, or stars being born in clouds of luminous gas. That child carries forward the spark of curiosity that Hubble helped kindle, ensuring that our exploration of the cosmos will continue long after the telescope itself has become history. The universe that Hubble revealed to us is vast beyond imagination, beautiful beyond description, and filled with mysteries that will challenge and inspire countless future generations. The telescope showed us that we live in a cosmos where the extraordinary is ordinary, where beauty exists on every scale, from the intricate structures of planetary nebulae to the vast web of galaxies that stretches across billions of light years. Most importantly, Hubble taught us that we are not separate from this cosmic magnificence, but part of it. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in the nuclear furnaces of ancient stars and scattered through space when those stars died. We are quite literally made of stardust, temporary arrangements of cosmic material that have somehow learned to wonder about their own origins. This perspective, more than any specific discovery or beautiful image, may be Hubble's greatest gift to humanity. The telescope helped us understand that we are the universe becoming aware of itself, consciousness emerging from the same physical processes that create galaxies and stars and planets. We are not observers of the cosmic story, but participants in it, characters in an ongoing narrative that began with the Big Bang and continues with every child who looks up at the night sky and wonders what's out there in the dark. As you drift towards sleep tonight, perhaps you'll spare a thought for Hubble, still circling overhead in its patient orbit, gathering light from distant stars and sending it back to Earth, where it will become part of humanity's ever-growing understanding of the beautiful, mysterious, infinite cosmos we call home. The telescope may be aging, but the wonder it inspired will continue forever, carried forward by everyone who has ever felt their hearts skip a beat at the sight of a spiral galaxy, or a stellar nursery, or the pale blue dot of Earth suspended in the cosmic dark. And so we come to the end of our gentle journey through the story of Hubble, a tale that began with a dream of perfect vision and led us through failure and triumph, heartbreak and wonder, to a place where we can finally see the universe as it truly is. As you settle deeper into whatever comfortable spot you've chosen for this cosmic voyage, perhaps you're feeling that particular kind of sleepy contentment that comes after hearing a story that somehow makes the world seem both larger and more intimate than it was before. There's something deeply satisfying about following a narrative from its humble beginnings to its profound conclusion, watching as human dreams transform into mechanical reality, witnessing the patient work of thousands of people united by a shared vision of what might be possible if we just refuse to give up. Hubble's story reminds us that our most ambitious dreams are often the ones most worth pursuing, even when, especially when, they seem impossibly difficult to achieve. Tonight, as you prepare to drift towards sleep, that remarkable telescope continues its eternal vigil overhead, travelling at 5 miles per second through the cosmic dark, its perfect mirror gathering photons that have been journeying across space for millions or billions of years, just to reach this moment, this intersection of human curiosity and cosmic light. Each photon that strikes Hubble's mirror carries information about distant worlds, ancient stars, and the deep structure of space and time itself, messages from the universe waiting patiently to be decoded by minds capable of wonder. The transformation that Hubble brought to human consciousness extends far beyond any single discovery or beautiful image. The telescope gave us something more precious than data or photographs. It gave us a new way of seeing ourselves in relation to the cosmos. We are no longer inhabitants of a small world surrounded by mysterious lights, but conscious participants in a universe of breathtaking scope and beauty, temporary arrangements of stardust that have somehow learned to contemplate their own origins. This cosmic perspective, more than any technological achievement, represents Hubble's most lasting gift to our species. The children who grew up with Hubble's images on their bedroom walls carry within them an intuitive understanding of cosmic scale that no previous generation possessed. They know, without thinking about it, that we live among the stars rather than beneath them, that our solar system is one of countless others scattered throughout our galaxy, that our galaxy is one of trillions dancing through an expanding universe filled with wonders we're only beginning to discover. When you look up at the night sky now, whether from your backyard, a city street, or through a window where you're lying comfortably in bed, you're seeing it through eyes that Hubble helped open. Those points of light aren't just pretty decorations scattered across a cosmic dome, but actual suns with their own families of worlds, their own stories of birth and evolution and eventual death. Some of those stars are stellar nurseries, where new suns are condensing from clouds of gas and dust. Others are ancient giants in their final moments, preparing to scatter the elements of life across interstellar space. The darkness between the stars, which once seemed empty and forbidding, is now filled with possibility. We know it contains vast networks of dark matter that provide the scaffolding around which galaxies form. It holds the expanding shells of gas from ancient supernovae, still carrying heavy elements toward places where new stars and planets will someday form. It resonates with gravitational waves from colliding black holes, carrying information about events so violent they warp the fabric of space and time itself. This is the universe that Hubble revealed, not empty and hostile, but rich with structure and meaning, governed by physical laws we can understand, filled with beauty that speaks to something deep in human nature. It's a cosmos where the extraordinary is ordinary, where phenomena that challenge our imagination are happening constantly, where every handful of seemingly empty space contains enough matter and energy to power civilizations we can barely conceive. Yet for all its vastness and strangeness, this universe is also profoundly intimate. The oxygen you're breathing was exhaled by ancient stars. The calcium in your bones was forged in stellar furnaces that burned out billions of years ago. The iron in your blood was created in the heart of a dying star and scattered through space in a supernova explosion that lit up some distant corner of the galaxy long before Earth even existed. You are not separate from the cosmic story, but woven into its very fabric, made from the same materials that create galaxies and planets and the most distant quasars that Hubble has ever observed. This connection between the cosmic and the personal, between the infinite and the intimate, represents perhaps the most beautiful aspect of what Hubble has taught us. We've learned that consciousness is not an accident or an intrusion in an otherwise mechanical universe, but a natural consequence of cosmic evolution, matter organizing itself into patterns complex enough to wonder about their own existence, to create tools capable of seeing across billions of light years, to ask questions about the origin and fate of everything that exists. The telescope that began as humanity's most expensive mistake became our most beloved success, demonstrating that even our most spectacular failures can be transformed into triumphs through courage, persistence, and an absolute refusal to accept defeat. The story of Hubble's rescue is also the story of human resilience, of our capacity to face seemingly impossible challenges and find ways to overcome them through cooperation and ingenuity. As you drift towards sleep, carried along by the gentle rhythm of your own breathing, you're participating in processes that connect you to the deepest patterns of cosmic evolution. The carbon dioxide you exhale will eventually find its way into plants that will use it to build leaves and flowers and fruit. The water in your cells will cycle through countless forms over the eons, rivers and clouds, ice and vapor, perhaps even the atmospheres of distant worlds that haven't been born yet. The atoms that make up your body have been part of stars and planets, comets and cosmic dust clouds, constantly recycling through different forms but never destroyed, never truly lost. In the deepest sense, you are the universe experiencing itself subjectively, a brief but beautiful flowering of complexity in the ongoing cosmic story that began with the Big Bang and will continue for trillions of years into a future we can hardly imagine. Hubble showed us that this story is far from over. The telescope revealed a universe that's still expanding, still evolving, still creating new wonders on timescales that dwarf human civilization. Galaxies are still colliding and merging, creating new generations of stars. Planets are still forming around young suns, perhaps some of them developing the conditions necessary for life to emerge and evolve and eventually wonder about its own origins. Somewhere in the cosmic dark, perhaps, other forms of consciousness are looking up at their own night skies with their own versions of wonder, building their own telescopes, making their own discoveries about the magnificent universe we all share. If they exist, they're seeing some of the same stars we see, governed by the same physical laws, made from the same cosmic materials, participating in the same ongoing story of matter and energy, becoming aware of itself through countless different forms of organization and complexity. The questions that Hubble has answered have led to new questions that future telescopes will explore. The James Webb Space Telescope is already revealing galaxies that formed when the universe was younger than we thought possible, challenging our understanding of how cosmic structure emerged from the smooth afterglow of the Big Bang. Future instruments will probe even deeper mysteries, perhaps discovering signs of life around distant stars, or detecting the gravitational whispers of parallel universes, or revealing aspects of reality that we haven't yet learned to imagine. But no matter how sophisticated our future telescopes become, no matter how much deeper they allow us to see into space and time, Hubble will always hold a special place in the story of human consciousness. It was our first clear window into the cosmos, the instrument that showed us what the universe really looks like when viewed with perfect clarity. It transformed abstract astronomical concepts into visceral reality, making the infinite accessible to finite minds, bringing the distant close enough to touch the heart. The images that Hubble captured will outlast the telescope itself, becoming part of humanity's permanent heritage, visual poems that capture the beauty and majesty of the cosmos in ways that words alone could never convey. Future generations will look at the pillars of creation, the deep field surveys, the portraits of dying stars and colliding galaxies, and feel the same sense of wonder that filled the hearts of those who saw these images for the first time. Rest now, knowing that above you the universe continues its patient dance, stars being born and dying, galaxies spinning through the cosmic night, dark energy pushing space itself apart, while gravity works to hold local structures together in an eternal tension that somehow gives rise to all the beauty and complexity we call existence. Hubble continues its vigil, sending back its quiet messages about the wonders that surround our small world, adding new verses to the ongoing poem of cosmic discovery. Sweet dreams, fellow travellers through space and time. The universe is vast and beautiful and strange, filled with mysteries that will inspire countless future generations to look up at the night sky and wonder what secrets remain to be discovered among the stars. And thanks to Hubble, we're finally beginning to find some of the answers to questions that have haunted human imagination since our ancestors first looked up at the cosmic dark and dared to dream of perfect vision among the infinite light. This is the Sleepy Astronomer, wishing you the most peaceful rest beneath the gentle glow of moonlight and starshine, and reminding you that you too are part of this cosmic dance of light and shadow, forever woven into the infinite story of the night sky.